So the final thing I want to talk about today is the concept of inductors. It's another electrical component that we'll consider in depth next. In the second half of this semester, we'll look at circuit analysis in more detail. And then we'll solve problems with resistors, then we'll move on to transients and AC circuits, and we'll look at inductors and capacitors. But I just want to introduce today the fundamentals of what an inductor are. And I guess so far you've looked at two types of circuit elements. We've looked a bit at resistance, and basically that's how hard it is to flow current through a conductor. And we defined resistance in terms of different parameters. Can you remember? We revised it on Wednesday. Resistivity and geometry, length and cross-sectional area. So parameters. We'd also looked at capacitance, and we defined capacitance as basically the ability to store charge in a parallel plate system. And we defined capacitance as the ratio of the charge stored to the voltage, Q equals CV or C equals Q over V. And so that the capacitor stores energy in the electric field. So basically you charge up a capacitor. The inductor is a similar type of animal, I suppose. Basically you're storing energy, but not in the electric field in the capacitor, but in the magnetic field in the inductor. So an inductor can be schematically thought of as a little small solenoid where we coil up a wire. If you coil up that wire and flow a current through that wire, there's going to be a magnetic field built up in the solenoid. Those magnetic field lines, you're going to have to do some work to build up that magnetic field. And in doing that, you're actually storing energy in the magnetic field. And that's what we mean by the concept of inductance. So instead, in the capacitor, it was charge and voltage. In the inductor, it's going to be current and magnetic field. Because in the static case, you're just moving charges in the capacitor. Here we have to have a flowing current to have a magnetic field. So several weeks ago, if you think back, we defined a capacitor capacitance. And we basically said it was a relationship between the charge and the voltage in an electrostatic system. And if we moved another charge from one plate to another, we had to do some extra work. And every time we moved one charge, we had to do some additional work. So capacitance was an electrostatic thing. Inductance is defined in terms of a relationship between a moving charge, which is the current, of current and magnetic field. Okay, because remember V, voltage, is essentially electric field. Electric field is volts per meter, so it depends how far apart the plates are. So this one depends on electric field. This one's going to depend on magnetic field. To give rise to magnetic field, we know we need a changing charge flow, or we need a current. Okay. So if we consider a little solenoid, which remember is just a wire that we wrap round and round many times. And this gives rise to the symbol for the inductor. It's just a little coiled wire. I know if I flow a current through that, so if I inject some current, and depending which way I've drawn the turns, I'm going to generate a magnetic field through this. So there'll be some magnetic field lines generated through this. And you can get the direction from the right-handed rule depending on which way you've drawn this. Current goes up, round and back. Yes, maybe they go the other way I've drawn it here, but a bit unclear which way the coil goes, but essentially your right hand, follow the current with your thumb, it'll give you the direction of the magnetic field lines. So we define inductance as the letter L is defined by an equation. An equation just looks at how much magnetic field is flowing through this solenoid. To be a bit more precise, we actually look at the flux, because the solenoid is a series of little loops. Each loop has got an area, it's got a cross-sectional area. So we'll say we've got a cross-section area in here. If I take one of these loops and it's a circle, I know the area, and I know the B field, so I know the flux. It's just the flow of magnetic field through the areas, and if it's along the center of a solenoid, B and dA are going to be parallel to each other, so B dot dA is going to be B times A. A is the area of a loop. So we're going to define it as the flux divided by the current. Now, we said earlier that solenoid, the good thing about that was I took the same wire and I looped it around many times. So if the wire goes in n circles, I'm going to essentially multiply the flux flow by n times. Each loop, if it's going in the same sense, is going to add up. So more formally, we actually put number n here. So this is the number of loops of wire. So that would be n equals number of loops. So this we compare with this definition here. So C was just the ratio of the charge and the voltage stored in an electrostatic field. Slightly different here because this is our flux, it's on the top this time, and the current is on the bottom, whereas the charge was on the top there and the voltage was the other way around. So we'll come back to that next half of the semester when we start looking at these in a bit more detail as circuit elements. Okay, so if we defined a new unit, a new element, we need to look at the units. So the units of inductance are, yeah, so you can get that from looking at this. So that is correct. It's Teslas per meter squared per amps. But that's got its own unit because we use it again and again. Actually, I don't remember that one. Henry is what we use typically. So it's 1 Henry or 1 H equals 1. So 1 Henry. So 1 Tesla meter squared per amp is 1 Henry. So a measurement of the flux through the solenoid. Okay, so this is our general equation that looks like this. It tells us what electrical, magnetic, or electrical charge type things are related. But what I'd like to know is the value of this. If I give you a capacitor and I know the area and I know the separation, it's a parallel plate, you can work out the capacitance and then charge stored, etc. So can I do the same for inductance? Can I work out an expression that tells me the inductance of a solenoid that I could then use if I had a circuit to analyze? Okay, so let's remove that. So let's see if we can work out inductance. So a solenoid is just this curled up wire. Okay, well, let's start with this equation. Let's write it in a slightly different format. We'll just say n times the flux. Okay, so n is the number of turns. So if I go along, count them 1, 2, 3, 4, 5, up to 25,000, that's the number of turns. We've got another way of defining the number of loops of wire, and that was, number of turns per meter. So that's maybe an easier one. And actually, when you buy these elements, they actually have turns per meter on them, because it's a slightly easier one. So let's say it's small n times, and we'll say curly L for the length of it, because capital L is going to be our inductance, so I guess we have to be a bit careful with symbols. Times the flux. What's the flux? Well, some integral of B dot dA. B and A are the same direction in a solenoid. B is constant in the solenoid, close enough to. A is the cross-sectional area, so let's just call this B times A. So that's B times A. And that's going to equal the inductance times the current. So I've just really rewritten this equation and plugged some other values in. But if you think back 2 or 3 lectures, we worked out the magnetic field due to a solenoid. And that was mu naught I times small n, number of turns per meter. So we could plug this into there. And that would tell us what? That would tell us the inductance times the current is going to be, no, just going to say the inductance is this equation. It's n phi over the current. This is my n phi up here, so that's n small l B times A divided by the current. Okay, so I've just plugged in for this. I can substitute for magnetic field now. That would be N times L. B is going to be mu naught I times N. I still have area, and I have current. Okay, so the only thing I've changed is B, and I've used the field for a solenoid. So what happens? Well, the I's cancel out, and L, the inductance, is mu naught N squared L times A. Yeah.
So small n is the turns per meter?
Yeah, small n is turns per meter. Capital N is the physical number of turns. So small n times L equals capital N. So if you look at this and compare it to the resistance of a wire, the resistance of the wire just depends on the resistivity times the length, and so longer wire, bigger resistance, and then divided by the cross-sectional area. The capacitance for a parallel plate capacitor, well, it was epsilon naught area over distance. So here I've got something, inductance, again, is mu naught, the parameter that relates magnetic fields to currents, and the rest of the stuff in here is geometry. It's number of times you've wound the wire per meter and the cross-sectional area. So again, it depends on geometry. Okay, I want to talk about two other things today. One is the concept of self-inductance. So we've considered problems where you've got a coil of wire. And that coil of wire creates a magnetic field in steady state. So if I'm running a current of 1 amp through here, I'm going to get a certain magnetic field. And I know if I put another coil over here and that intercepts the field or the flux lines from the first, Faraday's law tells me I'm going to get an EMF, and that if I've got a circuit will give me a current, and I know how to work that out. But if you think about the problem now, if I start with a battery and maybe a resistor and a coil in a circuit, so let's think of a very simple circuit structure. So let's say we've got a battery, and then we'll have some resistance because the battery and the resistor will have a small finite resistance. And then this comes round, and I'm going to have my solenoid. And I connect them together, and I've got a switch. Okay, if I close the switch, what happens? Well, I could argue that at the time I close the switch, or just before I close the switch, there's no current flowing. So I equals 0 because there's no potential, and the circuit is not switched on. I could imagine after a long period of time that if I have an EMF or voltage applied here from the battery, after a long period of time, end of the lecture, you've waited for an hour, I would have a constant current flowing through this. There'd be no changing current, and I'd be able to say, well, the resistance of this thing here, the inductor, would be, that's a question. Resistance of the inductor is 0. It's just a wire curled up. It's no resistance. The resistance here, well, we can say it's got R, some resistance R. So I know V equals IR would apply. So I'm going to get a certain current flowing around this circuit. So before t equals 0, nothing happening. After t a long time, constant current flowing in this. What happens immediately after I close the switch? So t, just a milli-micro nanosecond after I close the switch. Well, as the current begins to flow, it goes from 0 to a finite value that it would have after a long period of time. So the current changes. So as I close the switch, the current goes from 0 to I, given by this value. So there's a change in the current. It could be a step change, or it could be a gradual change. We don't care. If I've got a change in current, what do I have? I'm going to have a changing magnetic field in here, because the magnetic field lines here are going to change. The concept of self-inductance comes up because this coil here now sees a changing flux through it. So I've just got one coil. I'm generating a magnetic field that's building up from nothing as the current begins to pick up from nothing. So I've got a build-up of the magnetic field. That build-up of the magnetic field is a changing flux. And I know a changing flux gives me a EMF. So that EMF is going to try and stop the current flowing in this circuit. So it's going to push back. So the current doesn't easily start flowing. You have to actually do some work to start the current flowing, because the inductor wants to stop the flow of current. So you have to do work. You have to apply energy or supply energy to the inductor to get the current flowing. Conversely, after this has been sitting here for an hour, and I open the switch, or I take the driving and the potential away, the current really wants to keep on flowing in the inductor. Because if it stops, it gets a changing flux in the opposite sense, and that's going to still try and continue and drive the current. Now, this is maybe not a good example because I break the whole circuit, but you can, we'll analyze some variations on a theme later. So this is what we call self-inductance. Let's move this. So we have the idea of self-inductance. So, and another way of looking at the way the book actually analyzes it is slightly similar, but essentially the same. It basically takes a battery connected to one coil. Maybe we should put a resistor in. Has a second coil here connected to an ammeter or voltmeter. As I close the switch here, current begins to flow. The first solenoid generates a magnetic field. That magnetic field is picked up by the second coil. That produces a potential. That potential drives a current in the second coil, which creates a magnetic field in the second coil, which influences the first coil. So there's an EMF in the first coil through the presence of the second coil. So it's the same idea. The magnetic field, or the changing flux through the inductor, tries to set up a potential. So for any inductor we know, we have an equation that says N phi B equals the inductance times I. I've just rewritten the definition of inductance that we had, the first equation we wrote down, I think. But we know if there's going to be a changing, if there's an EMF set up in this system, Faraday's law tells me how to get that. It tells me that the EMF in the inductor would be just negative d phi B by dt. And if I've got an inductor that's got many coils or many turns, I should multiply that by n, which would be the same as saying equals negative n d phi by dt if I've got an inductor that's got more than one coil. So you'll see both. You'll see changing flux, or you'll see the flux multiplied by n in some cases. Okay. So we know what that equals. Just equals L times the current. Does L change with time? It's Friday before reading week. No, we defined L as something that depends on mu naught and the geometry. So the geometry is not changing, mu naught's constant, so L is a constant. So the field induced will be negative. I replace n and phi from here with L di by dt. So the EMF induced in the coil is proportional to the rate of change of current. So the faster I turn on the current, the harder it is going to be to drive the current through the inductor. If I have a very gentle change of current, it's going to be easier. And the direction comes from the negative sign and comes from Lenz's law. And that comes from the fact that as I start driving a current that is perhaps going this way through a solenoid, I'm going to set up one set of magnetic field lines that come from the right-handed rule. Lenz's law tells me that flux through the coil generates an opposing B field that's going to try and generate a current flowing in the other direction. So now as I drive the current, I've got the current from the battery going in one direction and the current from the changing EMF trying to oppose it in the other direction. And the size of that opposing EMF or current will depend on the rate of change of the current flowing through the system in the other direction. Okay, well, let's look at that in a little more detail and see if we can maybe relate that to the energy stored in the system. So, where to go? I'm going to redraw this picture again. I'm going to draw the battery here, and it's got some EMF, or we could call it some voltage. It's applied. It's going to be a plus, that's going to be a minus. Let's have some resistor and some inductor. It looks like this. So we've got some voltage, and we'll say that positive at the top, negative at the bottom, because the current wants to drive that way around the circuit. If this has got a resistance R, I know I'm going to have a certain power drop across there if I know the current and the voltage across it, or the current and the resistance. And this is going to be my inductor L. And when I have a changing current, this EMF that I induce here, this thing, depends on di by dt, but it's going to be directed in the other direction. The EMF due to the inductor is going to try and oppose the current flow. It's going to try and reduce the voltage. So we can analyze this circuit and come up with an equation that describes what goes on. And this is what, introduction to next term, this is what we'll do looking at various circuits. We'll define Kirchhoff's laws next term formally, but he's got two laws. One is current law, and we hinted at that when we had current into a junction, and we said charge is conserved, so all the current, total net current into a node is zero, i.e. all the currents going in must equal all the currents coming out. His other law is the voltage law, that basically says if I start at any point on the circuit and I walk around the circuit, I get back to the same point, I'm at the same voltage. So that makes sense. So Kirchhoff's voltage law says the voltage increases and the voltage decreases around a loop have to add up to zero. Okay, so using that I can say, well, the only thing that's generating me voltage at the moment is this thing. So the voltage supplied by the battery must equal the voltage drop across the resistor and any voltage change across the inductor. So what does that equal? Well, I know the voltage here, and let's just put magnitudes and make sure that we've got the two sides matching. That's going to be L di by dt, and the voltage across the resistor V equals IR plus I times R. So very simple. I've gone around the circuit. I've got a voltage increase here, got some voltage decrease for this one, and some voltage change here. If I add them all up and get the signs correct, I'm going to end up with net zero voltage. Is all that equation is saying. Okay, so does that tell us anything? Well, let's multiply both sides by the current again. So I would have I times epsilon, or epsilon, the voltage, equals Li di by dt plus I squared times R. Okay, does that help us? Any equation, if it's a true equation, I have to say x apples equals x other apples. So the dimensions on both sides have to be the same. So the dimensions of each of these terms have to be the same. So what's voltage times current? Power. That's true. I squared R is also power dissipated in the resistor, so that looks good. So that tells me that that term, that Li di by dt, must be power. It's basically the amount of power stored or the amount of power dissipated in the inductor. And I could imagine after the current has stabilized, after a long period of time, di by dt becomes 0, because the current no longer changes as a function of time. There is a current there, but it's constant, so di by dt is 0. So after a long period of time, the energy change in the inductor is 0, and the energy delivered by the battery equals the energy dissipated by the resistor. So that makes sense. So looking at each of these terms, this is the rate at which the battery provides energy. So I epsilon rate at which battery provides energy. And the rate of change of energy is power, so it's a power, it's going to be in watts. Volts times amps are watts. I squared R, that's the power dissipated in the resistor, lost in the resistor. So therefore, Li di by dt must be a power, and it's the power change, the power stored in the resistor. So it's the rate at which magnetic potential energy is I'll just use L for inductor. So it's the rate at which energy is stored in the inductor. Okay, so if I know that, it's the rate at which magnetic potential energy is stored in the inductor. So if I use U for potential energy, the rate of energy storage must be du by dt. So that's how quickly I'm putting energy into the system, and that must equal IL di by dt. Or if we think of a small change of time or a small change of current, i.e. we measure a small change of current from 0 to 0.01 seconds, we could say du by dt, dUB is really the current times the inductance times the change in current. Physicists do this type of stuff. They get rid of the di's. Mathematicians hate it. But basically what I'm saying is over a small length of time, and a small length of time is going to be the same on both sides, so it would cancel out, there's going to be a small change in energy, and that small change in energy, well, I know it's I times L, but it's going to be related to the small change in current. So if I put real numbers 0 and 1 in here, this becomes 1, 0 and 1 in here. Yep. Yep. di. We have to stay awake and follow on in this class because things can go wrong. Yeah, so change of energy is a small change in current. So if I make that assumption, I can work out the total energy stored in the system now. So I'm just going to integrate from t equals 0 till I get a uniform current after some time t of du, and that'll tell me what the total energy will be. So integrating and I guess I'm going to go from 0 actually until it's completely stored or completely full of energy, is the integral from 0 till all the current is flowing L I di. So L is constant, it's easy. Integral of I is half I squared. So basically if I play around with that, I get UB is 1/2 L times I squared. And you can compare that to energy in a capacitor, Q squared over 2C. So the energy stored in a capacitor with a dielectric constant of, well, it doesn't matter, it's rolled into C, but really is only the charge stored squared divided by capacitance. Here it's slightly different form, but we're still storing energy in the magnetic field, and it depends on the current. Seem okay? Okay, so a capacitor stores energy in the electric field. An inductor stores energy in the magnetic field. So both devices will store energy. Now they both work slightly differently. I add charge to the capacitor and I have a change in current that builds up a magnetic field. And then once I've got a current flowing through the inductor, that flowing current in the inductor is going to create its own magnetic field. And that magnetic field doesn't want to decay, it wants to keep the current flowing because self-inductance doesn't want the current to stop. Questions? Happy? So that's really all I've got for you. We'll look at inductors and capacitors in more detail in 2 weeks' time when we reconvene for the second part of the course. The second part of the course is going to be the other half of the textbook, Irwin's book, and it's going to look more at electrical problems from a circuit engineering point of view. We'll look at resistors, capacitors, and inductors. So the electrostatics underpin the operation of the resistor and the capacitor. The magnetic fields underpin the operation of the inductor. Now we're going to use those components in a circuit geometry.